Hello all. In the last class we were discussing about some general definitions for second normal form, third normal form and BCNF. Today we'll discuss about some other topic from this database design, that is Armstrong's uh, inference rules. So these are the topics for today. We'll see some introduction for this, and we'll have a quick recap on this functional dependencies, then Armstrong's inference rules, and closure. So let's have we know that this relational database design can be done in two ways. The first one is, or the first strategy is by analysis, or you can call it as top down, and we have a relational database design by synthesis or bottom up. Okay, so what is meant by this analysis, relational database design by analysis or top down? Okay, so for designing this database, we start from this ER model, and from ER model we'll be able to develop or create relations and their attributes. Okay, and because this ER models will have entities and relations, and entities will have attributes, and these can be converted into our relations and their corresponding attributes. Okay, and we set up some specific conditions for these attributes, and if these conditions are satisfied, we can say that they are in first normal form, second normal form, third normal form, or in BCNF, like that. Okay, and in the case of relational database design by synthesis, or we can call it as bottom-up strategy, there we start from a universal relation or universal database, and from that we'll have some set of attributes. For example, if we have a college database or college relation, we'll have all the set of possible attributes there. For example, corresponding to a student, we'll be storing attributes like student admission number, name, then maybe student course, their previous grades, then their phone number, etc. And corresponding to the teacher, we'll be storing information like teacher's pen, that is permanent employee number, then maybe the subjects taught by this teacher, qualification of the teacher, or phone number of the teacher, etc. All this will be written, and from these attributes we'll be trying to figure out semantics of this attributes, which means we'll be trying to find out the relationships among this set of attributes, and we'll be able to find out functional dependencies for these attributes, and we can say that this will be in second normal form, third normal form, or etc. like that. Okay. And as I told you, we'll have a quick recap on this functional dependencies, and we know that how we can define this functional dependency. And a set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. Okay, we can say that we have a set of attributes X and another set of attributes Y, and we can say X functionally determines Y if the value of X determines a unique value for Y. And we can denote it like this: X determines Y. And this holds if whenever two tuples have the same value for X, they must have the same value for Y. That is a condition for this functional dependency. If two tuples have the same value for X, then it must have the same value for Y also. Okay, and for any two tuples T1 and T2 in any relation instance R of capital R, if T1 of X equal to T2 of X, then T1 of Y is equal to T2 of Y. That's what we said, and that is X functionally determines Y in R. Specify a constraint on all relation instances R of capital R. Okay, if we are giving x to y, or x functionally determines y, then it specifies a constraint on all relation instances R of capital R. And what is inference for this functional dependencies? Okay, so a functional dependency x to y is inferred from or implied by a set of dependencies f specified on R. So we are saying that a function dependency x to y that is inferred from or implied by a set of functional dependencies f. So we have a relation R, and for this R we are defining a set of functional dependencies f, and we can infer, or this is used to imply or infer some other functional dependencies. Okay, we'll see what is meant by that. And if x determines y holds in every legal relation state R of capital R, that is, whenever R satisfies all the dependencies in F, x to y also holds in R. Okay, so which means that x to y holds in every legal relation state R of capital R. It means that whenever R satisfies all the dependencies in F, x to y also holds in R. Okay, and given a set of functional dependencies f, we can infer additional functional dependencies that hold on whenever the fd's in f hold. Okay, if we have this set of functional dependencies f, and corresponding to this we'll be able to infer additional functional dependencies that hold. Okay, whenever the fd's in f hold. So for example, we have department number that determines manager SSN, then manager SSN determines manager underscore phone, then this inferred from or implied by department number implies manager phone. Okay, department number that implies manager SSN, then manager SSN implies manager phone. So which means department number implies manager phone. Okay, that we saw, that is the transitive relationship. So this we have two functional dependencies, and from that we can infer a new functional dependency like this: department number implies manager phone. Okay. Consider another example where we have a relation employee underscore department. So we have E name, SSN, D date, address, D number, D name, D manager SSN. All these are the attributes, and we have some functional dependencies written here. That is the set of functional dependencies, that is capital F, that is equal to, we can say that SSN implies, so this SSN is the primary key that implies E name, B date, address, then D number. Okay, and next functional dependency is from D number to D name, D manager SSN. So from this we can infer SSN implies D name, or SSN implies D manager SSN. Okay, or we can even say D number implies D name. Okay, or D number implies D manager SSN. Okay, so we have given some function dependencies, or a set of function dependencies f. From this f we can infer new function dependencies. Okay, and closure of FD. So we'll see what is meant by closure of FD. So closure of a set F of FDs is the set F plus of all FDs that can be inferred from F. So we said that if we have a set of FDs, capital F, so from this set we'll be able to infer new function dependencies. Okay, and what is meant by closure? And closure is again a set, and that is all FDs that can be inferred from this particular F. Okay, we have a set of dependencies, and we are saying that if we call that as F, then we will be able to define F plus also, which is nothing but the set of all FDs that can be inferred from this F. Okay, and for that we'll make use of some inference rules to determine a systematic way to infer dependencies. So we'll have some inference rules to determine a systematic way to infer these dependencies from the given set of dependencies. And when we talk about this inference rule, we'll see some notations also. So the first notation is like this. We have F and this notation that is used for representing inferred from or implied by. Okay. So we can say that F implies X to Y. Okay. Or X to Y is inferred from this F. Okay, so this is to denote that the function dependency X to Y is inferred from the set of function dependencies F. Okay, so that is we can say the function dependency, for example, X to Y, X comma Y to Z. Okay, you can use this abbreviation for that. This is abbreviated to X, Y to Z. Okay, even though that is a set, you can represent that with the juxtaposition X, Y to Z. Or if you have a function dependency like X that is set X comma Y comma Z that implies U comma V, then that can be written as X, Y, Z to U. Okay, so that is this, each one is a set. So you can use a juxtaposition like this X, Y, Z to U, V. Then we'll see Armstrong's axioms. Okay, so when we talk about these axioms in mathematics, we know that these axioms are some non-facts. Okay, but here these axioms are not this kind of facts. They're actually rules. Okay, inference rules. Okay, so axioms are inference rules. So we have 6 different inference rules. Okay, so what we are trying to say is that we have a set of functional dependencies, and from this functional dependencies we'll be able to infer other functional dependencies. And when you get all the functional dependencies from that set, that is known as closure of that particular set. And how will you infer this new functional dependencies from the given set of functional dependencies? That is by making use of this kind of axioms or inference rules. Okay, so the first inference rule, that is IR1, that is also known as reflexive rule. Okay, reflexive rule, and that says if X is a superset of Y, then X determines Y. Okay, or if Y is a subset of X, X determines Y. Okay, so that is if Y is a subset of X, then X implies Y. That is, a set of attributes always determines itself or any of its subsets. Okay, so we have a set of attributes that always determines itself or any of its subsets. So we have Y, which is a subset of this X. So we can say that any set of attributes will determine itself or any of its subsets. Okay, so here Y is a subset of this X. So we can say X functionally determines Y. Okay, for a functional dependency X to Y is trivial if X is a superset of Y, otherwise it is non-trivial. Okay, so that is by default when we can say that a set of attributes always determines itself or any of its subsets. That's why we say function dependency X to Y is trivial if X is a superset of Y or Y is a subset of X. Otherwise only this function dependency is non-trivial. Okay, so let's see some example for inference rule 1. That is, consider a student relation with attributes admission number, name, DOP and address. Okay, so admission we'll be able to define some functional dependencies. For example, admission number comma name, that implies name. Okay, so here what we say is X is a superset of Y. So here what is X and what is Y? X is admission number comma name and Y is name. So here this name is a subset of admission number comma name. So this function dependency will always, that is admission number comma name implies name. Okay, which means name is a subset of admission number comma name. And the reflexive rule can also be stated as X implies X. Okay, that's what we said. A set of attributes are always determine itself. Okay, so this can be stated, or the reflexive rule can also be stated as X implies X. So any set of attributes functionally determines itself. Okay, that is name to name or admission number to admission number. Okay, that is by default. This is the first inference rule, that is reflexive rule. Okay, and we have the second inference rule, that is also known as augmentation rule. Augmentation means we are adding something to the existing rules. Okay, so IR2 is the augmentation rule, which means suppose we have a function dependency like X to Y. Okay, that is a function dependency. So this implies, or we can infer this from the left hand side. So what this infers, X Z implies Y Z. Okay, so we have X implies Y, so that implies X Z implies Y Z. Okay, so which means you are adding another attribute Z on both sides. Okay, then this will also be true. So adding the same set of attributes to both the LHS and RHS of a dependency results in another valid dependency. So what you get? You get another valid dependency. Okay, and can also be stated as, that is, augmentation rule can also be stated as X implies Y, that implies XZ implies Y. Okay. Okay, X implies Y. You can infer from this X Z implies Y. So augmenting the left hand side attributes of an FD produces another valid FD. Okay, so you can even add attributes on the left hand side, that will also produce another valid FDs. Okay, so augmentation rule means either you can add the same set of attributes to both the LHS and RHS of a function dependency, or you will be able to add attributes to the left hand sides. Okay, then in these two cases you will get another valid dependencies. Okay, and example for IR2 augmentation rule, that is student relation student with attributes admission number comma name comma DOB comma address. So these are the attributes. So we are defining one function dependency, or one function dependency is given like this: admission number implies name or determines name. So as per IR2, the second rule, we will be able to infer admission number comma DOB implies name comma DOB. So with DOB, that is date of birth, on left hand side, and RHS right hand side, and you will be able to get a valid dependency. So admission number comma DOB implies name comma DOB, or that determines name comma DOB, or admission number comma DOB determines name. Okay, so you'll be able to get name from admission number comma DOB. Either you can add the same set of attributes to both LHS and RHS, or on the LHS. Okay, so you have two examples for IR2. And next we'll see the third inference rule, that is transitive rule. We are familiar with this transitive rule. Anyway, IR3, that is known as the transitive rule. There you have X implies Y, or X determines Y and Y determines Z. So you can infer from this X determines Z. Okay, that is known as transitive rule. X determines Y, Y determines Z. You have X determines Z. And let's see some example for this IR3. again you consider employee underscore department relation. So you have E name, SSN, B date, address, D number, D name, D manager, SSN. And you have some function dependencies like SSN implies or SSN determines E name, B date, address, department number. And you have department number determines D name, D manager underscore SSN. Okay. And from this you will be able to infer. So here look at this. You have SSN. From SSN you have SSN determines D number determines D name. So you can write SSN determines D name or SSN determines D manager underscore SSN. Okay. And we can say that this inference rules from 1 to 3. The first to third inference rules as sound. Okay, you can call it as sound and complete. So what is meant by sound? There's a inference rules 1, 2 and 3 are sound. Okay, that is given a set of function dependencies F specified on R. So we have given a set of function dependencies F specified on R. Then any dependency that is inferred from F by using IR1 through IR3 will halt in every relation state. Okay, that's why it is known as a sound. So suppose you have a function dependency, a set of function dependency F, and any dependency that is inferred from this F by using IR1 through IR3 will halt in every relation state. Okay, when you consider every relation state, this IR1 or the dependencies that are inferred from F by using IR1 through IR3 will halt in every relation state. Okay. And you can also say that this IR1 to IR3 is complete. That is applying IR1 through IR3 repeatedly on F. Okay, suppose you repeatedly apply IR1 to IR3 on this F. So results in the complete set of all possible dependencies that can be inferred from F. Okay, so what will happen? You will get a complete set of all possible dependencies that can be inferred from F. That is, you will get F closure. That is, closure of F can be determined from F by using only inference rules IR1 through IR3. Okay, suppose you have again a set of dependencies F, and you keep on or repeatedly applying IR1 through IR3. So we'll get a complete set of all possible dependencies that can be inferred from this F, and that is nothing but closure of F. Okay, and the fourth inference rule is IR4, that is also known as decomposition or projective rule. Okay, decomposition or projective rule. So that is IR4, that is like this. Suppose you have function dependencies like X determines YZ. Okay, that implies X determines Y. Okay, which means you have function dependency like X determines YZ. Now you are trying to decompose it. So you'll get X determines Y or X determines Z. Okay, so you have X determines YZ. From that you get X determins Y. Okay, so that is X, for example, X determines the set A1, A2, etc. AN. Now you can decompose this into some dependencies like X determines A1, X determines A2, etc. X determins AN. Okay, so you have admission number determines name, comma, DOB, comma, address. For example, consider that you have again this previous relation. From that, admission number determines name, comma, DOB, comma, address. Okay, now you have admission number determines name, admission number determines DOB, admission number determines address. Okay, you will get 3 function dependencies from the given dependency. Okay, so admission number to name. So you are decomposing that into 3 different dependencies. And the fifth inference rule, that is opposite of this decomposition, that is union or additive rule. Okay, so that is I of 5. There, suppose you have x determines y and x determines z. Okay, see the left hand side is same. X determines y and x determines z. So you will be able to write it like this: x determines yz. Okay, x determines y, x determines z. So you get x determines yz. And x determines a1, x determines a2, etc. X determines a. Then how will you write? It is like x determines a1, a2, etc. a. Okay, that is you are performing union on this function dependencies. Okay, and you will be able to get one single function dependency from a number of function dependencies. Okay, so for example, admission number determines name, comma name, and admission number determines DOB, admission number determines address. Okay, so that is admission number determines name, comma DOB, comma address. This is actually opposite of the decomposition rule, that is IF4. Okay, now we have the sixth inference rule, that is known as pseudo-transitive rule. Pseudo-transitive rule. And that is, suppose you have x determines y and wy determines z. Okay, x determins y, wy determines z. Now what we will do is you will replace this y with x. Okay, now you get wx determines z. Okay, so x determines y, wy determines z. You replace y with its left hand side, that is x. So you'll get wx determines y. It is the pseudo-transitive rule. Okay, so this allows you to replace a set of attributes y on the LHS of a dependency with another set x that functionally determines y. Okay, you will be able to replace a set of attributes y on the LHS of a dependency with another set x that functionally determines this particular y. Okay, that is, for example, student relation with admission number, name, DOB, and address. Okay, suppose you have admission number determines DOB and name, comma DOB determines address. So from this, you will be able to replace this attribute on the LHS of this dependency with another set x that functionally determines this particular y. Which determines this DOB? Admission number determines DOB. So name, comma admission number that determines address. That is another function dependency. Okay, so that is known as a pseudo-transitive rule, IR6. And you should note these points. For example, suppose you have function dependencies like x determines a and x determines y. That implies x determines AB by the union rule stated above. Okay, suppose you have x determines A and x determines B, you will be able to write x determines AB. Okay, and suppose you have x determines A and y determines B, that implies xy determines AB. Okay, suppose you have x determines A, y determines B. That is different symbols on LHS and RHS on different function dependencies. In that case, you will be able to combine them and write the function dependencies. So from these two function dependencies, you will be able to write a third function dependency, that is xy functionally determines AB. Okay, and here consider this: xy functionally determines A. Xy functionally determines A. That does not necessarily imply either x implies A or y implies A. Okay, so from this we know that when we have x and y together, we will be able to determine A. Okay, so you should not, or you are not allowed to split this x and y. You cannot write x. This does not necessarily imply either x determines A or y determines A. Okay, that splitting is not possible. And Summary means we discussed about IR1 inference rule, that is reflexive rule, then IR2 that was augmentation rule, then IR3 transitive rule, IR4 decomposition rule, IR5 union, and IR6 is pseudo transitive rule. Okay, so that is all for today.